So our next speaker is Kamryn Mcleran. Let's go, Kamryn. Kamryn came to us as an environmental scientist with a focus on aquatic toxicology and wildlife conservation. She decided to do a capstone project that really played to those strengths and allowed her to apply them in new ways. She's very modest, but don't be fooled. She did an extraordinary amount of work for this project, and this is just a sort of teaser, right to my right on this table, of what you're going to hear about today. So join me in welcoming Kamryn Mcleran.
Throughout my professional and academic career, I have worked in the field and in the lab, trying to understand how to protect our environment. I quickly realized I have a passion for water quality and wanted to continue my career finding solutions to keep our coastal waters healthy. When I started this program, I figured I would end up with a project involving water quality, but I never imagined it would lead to building this robot. While searching for a capstone project, I connected with the nonprofit California Trout, which is an organization dedicated to revitalizing the state's waters through science, restoration, community engagement, and advocacy. Despite substantial investment in coastal lagoon restoration, there's often no clear, accessible method for evaluating whether restored habitats are actually chemically and biologically suitable for native species. Understanding parameters such as pH and salinity can help us understand if our native fish can actually survive in the habitat once it's done being restored. To solve this, I took on the task of developing a tool for California trout's ultimate purchase and use that could autonomously enter the water and collect data to help us better understand the health of the lagoon. It was very important to us that collaboration and outreach were at the forefront of this very technical project. Community involvement is key to the success of restoration projects, and it can help us foster a sense of trust in the people who will be most affected. With all that in mind, we settled on using the Buena Vista Lagoon as a case study for this project. It will act as a model for this tool's eventual expansion to other bodies of water with their own environmental monitoring needs. Because the Buena Vista Audubon Society has an interactive nature center located at the lagoon, and because of its proximity to various schools, we knew we had the potential for involving the community throughout the entire process as well. So this is the Buena Vista Lagoon, and it's located between Carlsbad and Oceanside, and is Southern California's last freshwater lagoon. In the 1940s, the local landowners placed a small barrier at the mouth of the lagoon, which was reinforced in the 70s. And this barrier restricted the lagoon from any tidal flux, resulting in a fully freshwater system. Since then, invasive plants and animals have taken over the lagoon, and it's become a breeding ground for mosquitoes. Not only is this degrading the habitat, but it's also negatively impacting the local landowners. For almost 20 years, the California Department of Fish and Wildlife, local landowners, and other stakeholders have debated on the best steps to handling this lagoon, by either fully restoring it to a pre-1940s saltwater system, leaving it as a freshwater system, or finding an in-between. And as of today, the San Diego Association of Governments, or SANDAG, is in the planning process for restoring the lagoon to a system fully available to the ocean again. This tool could help us evaluate the success of habitat restoration, and by holding outreach events, we can ensure the community is aware of the changes to come and that they understand the importance of water quality analysis. So this project consisted of two main parts. There's a technical side, which resulted in a written technical report, and an outreach side, which resulted in a written and tested lesson plan for student involvement. And I'll start by going over the technology aspect now. When I began researching autonomous tools, my goal was to identify a solution that was cost-effective, user-friendly, and customizable, all to offer the flexibility needed for different organizations and agencies to be able to adapt it to their own monitoring needs. And with these goals in mind, I connected with a company called Blue Robotics and learned about their uncrewed surface vessel, or USV, called the Blue Boat. As a surface vessel, rather than an ROV that would be operated under the water, we could avoid any issues with highly vegetated lagoons, such as the Buena Vista Lagoon. The best part of the Blue Boat is that we could customize it to include a variety of monitoring sensors, and for our purposes, we were starting with water quality sensors. So when schedules aligned, I was able to meet the Blue Robotics team at their headquarters in Torrance, where I was able to construct my own blue boat to bring home with me. So after the almost 2-hour drive from San Diego, I arrived at a huge blue warehouse with a giant above-ground pool, collaborative picnic tables, and a team of engineers excited to help me. I was given a tour of the space and gathered up the equipment to build my own robot. I got set up in a cozy conference room, opened the box, and saw this, a daunting amount of equipment and wires. Luckily, I had a few helpers and the very easy-to-follow Blue Robotics assembly guides. Once the boat was officially a boat, I was on to the software setup, but of course, that is when my helpers had to get back to their real jobs. So for the next few hours, I connected antennas, charged batteries, and calibrated the boat's internal compass. Somehow this process was much easier than I was expecting, and I left with a boat that could turn on, connect to its base station, and its propellers could spin. This was a huge accomplishment, not just for my project's development, but for me as a scientist in a new field. Going through this process made it clear that even teams without a robotics background could replicate it, opening the door for widespread use. At the same time, I was researching water quality sensor kits and became connected with a co-founder of FieldKit. This company creates modular, low-cost stations that support environmental monitoring across multiple domains, including weather, water quality, and air quality. These kits have the software that allows for collecting, analyzing, and displaying data directly to your phone through a mobile app. And of course, we were most interested in the water kit, this included sensor probes for pH, dissolved oxygen, conductivity, and temperature. Sometime later, I picked up our own field kit and brought it home to put it all together. Again, this piece of technology was very easy to use and assemble. Both the Blue Boat and the field kit run on the same Raspberry Pi computer, which allows for very easy software integration. The field kit can also run as a standalone piece of technology, so it can simply be mounted to the boat externally, and we can see the data on separate platforms. And that's what we have done so far here. Next, I had to design a way to integrate the field kit probes with the Blue Boat so that they would still be submerged in water, but protected from any collision or getting damaged. And my first attempt resulted in placing 2 probes off each of the crossbars in their own respective corners, as you can see here. Once the field kit was mounted, it was time for our first test run in the lagoon. And luckily, it not only floated, but was able to successfully drive a predetermined route all on its own. The layout of the field kit probes worked better than expected, but I will continue exploring designs to provide added protection for the sensors. And fortunately, I'll have the chance to continue supporting CalTrout with this project even after graduation, and I look forward to refining the system further. Although we were building this tool to be used in the Buena Vista Lagoon, we still wanted it to be adaptable for other uses and bodies of water. So once my initial test runs were complete, I got started on writing a technical report. This report is meant to be a reference for any agency, local government, or organization to use when they are searching for their own monitoring tool. During my initial research, I met with managers and project leads from the California Department of Fish and Wildlife, SANDAG, AECOM consultants, and the Buena Vista Audubon Society. After sharing my goals for this project and its potential for expansion, it was encouraging to hear their excitement and their ideas for how they could adapt it to meet their specific monitoring needs. This report will also be distributed across CalTrout offices for regional use throughout the state, and they also plan to share it with colleagues who work in state agencies and environmental consulting who are involved in restoration and monitoring efforts. While constructing and designing the boat was exciting, I knew that this tool would have the most impact if the local community was aware of the Buena Vista Lagoon's restoration plan, and if they understood the importance of water quality analysis. California Trout will be hosting a community workshop at the end of the year at the Buena Vista Audubon Society and Nature Center. This is going to surround restoration, collaboration, and this new tool. Knowing this, I decided to develop a lesson plan that could be used at this outreach event or others like it that could engage the community and provide hands-on experience working with water quality. So I was fortunate enough to actually be able to test this lesson plan with 5 different classes of students from Carlsbad High School. This school is less than 10 minutes away from the lagoon, but most students had no idea the restoration was even being planned. I coordinated with the Buena Vista Audubon Society and Nature Center, as well as the AP Environmental Science teacher from Carlsbad High, to get all 5 classes of students to the lagoon. Over the course of 2 full days, I presented on the history of the lagoon and the 2-decade-long battle to get to this stage in the restoration process. After introducing the Blue Boat and explaining the key water chemistry parameters that we monitor for, I brought the students outside to collect real-time field data. While back in the classroom, we compared data from different areas in the lagoon and discussed why these values may vary and how they might change when the lagoon is open to the tides again. During our time together, we explored both the benefits and challenges of conservation and restoration work. It was incredibly rewarding to watch students engage with the material and connect it to their own surroundings, especially since many had no idea that their local lagoon was going to change. The real power of this project isn't just the technology, it's how we use it with people. A tool like the Blue Boat can support better data and smarter decisions, but its greatest potential lies in connecting communities to the restoration happening in their own backyards. When people understand the why behind restoration, when they see how water quality is measured, how decisions are made, and how technology like the Blue Boat plays a role, they become part of the process and not just observers to it. My favorite part of this project is the fact that this tool isn't just for one lagoon. It's adaptable, approachable, and scalable. I hope that this tool becomes a model for effective data collection and inspires more collaboration between scientists, conservation groups, and local communities. Because in the end, restoration is most successful when it's something we do with communities and not just for them. I want to thank my wonderful Capstone Advisory Committee for the guidance, support, and encouragement throughout the last few months. Dr. Sandra Jacobson, the Regional Director of Cal Trout and my chair, Dr. Amina Shartup, Scripps Associate Professor in the Marine Chemistry and Geochemistry Department, and Riley Meehan, the Director of the Scripps Makerspace. I'm incredibly grateful for the long list of people and organizations who helped bring this project to life in such a short amount of time. And lastly, I truly could not have gotten through this year without the support of my friends, family, and MAS MBC team. Thank you. Any questions? Yeah. I think there's a mic coming around.
So this is a real exciting project that you're doing here, but one of the things I think it might be related or be useful for is people in lake communities or reservoir communities, and you talked about it being scalable. Maybe there was something that could be developed individually for those communities so they could keep an eye on their water rather than just once a year testing by the Department of Resources. Just seems like something that could be marketed nicely.
Yeah, that's, I think, the whole goal. So working with Cal Trout, this technical report is something that I hope to spread to anybody and anyone who's looking for some tool that they can have for their own use. We know that most robotic stuff is very expensive in the hundreds of thousands of dollars, and something like this is in like the $5,000 range, and it's very accessible and very easy for local governments and small communities to have for themselves to do some testing. So that's definitely the goal, and we see a lot of progress, and it's going to be able to spread to far reach places. Yeah. Yes.
Kamryn, you did such a nice job of really taking a complex project and building the core configuration. Can you speak to the principle of what we see there is all these bars and chemistry? Once you start putting other things on it, like cameras, so you can see underwater species, correlate that with microchemistry within a lagoon or an estuary, sonar, et cetera. Can you speak to some of the possibilities of forward progress there?
Yeah, so definitely our next steps with this project, besides fine-tuning the setup of the kit that it already has, will be adding an underwater camera so that we can do species distribution surveys and see what's under the water, and are there species that are returning once the lagoon's restored, or any lagoon that it's going to be used in. But it's also a good education tool as well. When the boat is out in the water, it's going to be able to live stream that camera footage back and have the community and local students be able to actually see what's under the water, which is really exciting. Talking to the different environmental consultants and agencies that I did speak with, they were talking about adding bathymetry sensors and getting depth profiles of lagoons, which is a lot easier with a small boat like this to get into those small, hard-to-reach places with the large bathymetry sensor boat. So I think for now, we're going to start with the camera and go from there, but there's many sensors that can be added to this boat. Swap the different ones out, maybe add 2 at the same time, and get to really get the idea of what the lagoons and coastal waters look like. Thank you.
Great job, Kamryn.